All of you can give your attendance in the chat box. I repeat, all of you can give your attendance in the chat box. Now the time is 1:15 p.m. I will not wait further. So let us start the class. Let me present my screen first. Can anyone respond whether my slides are visible or not?
Yes, sir.
Okay. So let us start the class from where we left behind. In the last class, we were discussing this problem, third problem we were discussing, and we have done till equation number 7. That means we have calculated the value of domain residual for this problem. If anyone can respond. Hello. Can anyone respond? I think what I know is that we have in the last class we have did till equation number 7.
Yes, sir. Yes.
Fine. Okay. So once we have found out the value of this residual, then I need to find out the approximate solution for this problem by point collocation technique and by Galerkin technique. I know that in point collocation technique, how I minimize this residual. In order to minimize the residual, I will equate the residual value equal to 0 at n number of collocating points, and those collocating point will depend on what is the domain of your problem. If I see in this problem the domain varies from x equal to 0 to x equal to L. So in between 0 to L you can take n number of collocating points to get the approximate solution for this particular problem. So let us take, I have taken the collocating point as L by 4. Domain of the problem varies from x equal to 0 to x equal to L. You can take n number of collocating points. If you take n number of collocating points, and if you try to if you try to find out the approximate solution of the given differential equation, with that you can validate with the exact one. So I have taken the collocating point as L by 4. So I will make this residual, that is equation number 7, equal to 0 by keeping the value of x as L by 4. So let us keep it. So my residual is equal to 0. That means E into I C1 pi 4 upon L to the power 4 into sine of pi x by L. In place of x, I will write L by 4. So sine of pi into L by 4 by L minus Q naught is equal to 0, because this is the statement of point collocation method. Now L get cancelled. Sine pi by 4 is nothing but 1 by root 2, 45 degree, sine 45 degree, which is 1 by root 2. So the resulting equation becomes E into I C1 pi to the power 4 divided by L to the power 4 into sine of pi by 4 is 1 by root 2, and q naught I am taking it to the right hand side, which is equal to q naught. Now from this expression I can find out this unknown coefficient present in the residual. So the value of this unknown coefficient will be how much? It will be, just cross multiply it, you will get it as root 2 into q naught L to the power 4 divided by pi to the power 4 into EI, equation number 8. Any doubt in equation number 8? Any doubt in equation number 8? Please respond whether you are having any doubt or not till equation number 8. Hello. Hello. Please respond whether you are having any kind of doubt or not till equation number 8, or else I cannot proceed.
Yes, sir, no doubt.
Okay, fine. So now what I will do is that we will substitute this unknown C1 in the given trial function. That is, my assumed trial function is this one, that is equation number 1. V cap of x is c1 into sine of pi x by L. C1 I have found it out by point collocation technique, which is nothing but root 2 q naught L to the power 4 by pi to the power 4 into EI. So after substituting, your final approximated solution for the given differential equation by point collocation technique becomes root 2 q naught L to the power 4 upon pi to the power 4 into EI into sine of pi x by L. So this is the approximate solution of the given differential equation by point collocation technique. The second technique which we will be using is the Galerkin technique. And in Galerkin technique, we know that we have to multiply the weighted function, which is wi of x, with the domain residual, which is my equation number 7, and then the entire product we have to integrate it over the complete domain of the problem, and then this entire integral is equated to 0. This is the statement of Galerkin method. Fine. So in this Galerkin method, I also know that this weighted function is what? This weighted function is nothing but the assumed trial solution given in the problem. If it is given, well and good. If it is not given, then I have to assume it. So this is my assumed trial function. V cap of x is c1 into sine of pi x by L. So the weighted function will be c1 into sine of pi x by L, which is the assumed trial function. And R of x is what? R of x is my domain residual or error of the problem. That is nothing but my equation number 7. So let us multiply this equation number 7 with the weighted function. What I will get? I will get c1 into sine of pi x by L into domain residual, which is ei into c1 pi to the power 4 divided by L to the power 4 into sine of pi x by L minus of q naught into brackets d of x equal to 0. Now, in order to solve this integral, what I will do, I will multiply this term c1 into sine pi x by L firstly with this particular term, then minus of multiplication of this term with this q naught term. So let us multiply. So your equation will become domain integral 0 to L c1 square into e into I pi to the power 4 upon L to the power 4 sine square pi x by L. See, ei c1 square pi to the power 4 upon L to the power 4 into sine square pi x by L into dx minus this minus sign minus q naught into c1 sine pi x by l dx. See, minus integral 0 to l c1 q naught sine pi x by l into dx equal to 0. So this term, the second term, you can, or I can keep bring it towards my right hand side. If you bring it towards your right hand side, your equation will become, and this e I c1 square pi to the power 4 and l to the power 4 is a constant quantity. Keep it, take it out from the integration. Then it will become integral of 0 to l sine square pi x by l dx equal to C1, take it out from the integration, constant quantity, integral of 0 to L, Q naught into sine of pi x by L dx. This once this C1 and this square got cancelled, your final equation becomes EI C1 into pi by L whole to the power 4 integral of 0 to L sine square pi x by L dx equal to integral of 0 to L q naught into sine of pi x by L dx. Now just you have to simplify this integral equations. Very simple. Just if you solve this integral equation, you will get the unknown constant C1 by Galerkin technique. And that C1 comes out to be around approximately equal to 0.013071 q naught into L to the power 4 by EI. Now the approximate solution by Galerkin technique will be what? In the approximate or the assumed trial function, that means in this trial function I have to substitute the value of C1 which I have find it out by Galerkin method. So let us substitute the value of C1. So the resulting approximating solution for the given problem becomes V of x is equal to C1. C1 is 0.013071 Q naught into L to the power 4 by E1 into sine of pi x by L. So this is the approximate solution for the given problem by by Galerkin technique. Is the problem clear? Any doubt in the problem? Hello. Please respond whether the problem is clear or not. Hello.
Yes, sir.
Okay, fine. So let us solve one more problem. After that, we will wind up this weighted residual topic. Then we will move on to the next topic, next and the last topic for this module. So far, if you see, we have solved static structural problem. Now let us solve one heat transfer problem by this method, that is by Galerkin method, point collocation method, least square method. Let's see how we can solve a heat transfer problem by such methods. So let us understand what the problem is telling us. The problem is, consider a 1 millimeter diameter 50 long aluminium pin fin. This is your fin which is attached to a wall. Wall temperature is TW. Ambient temperature is T infinity. Convective heat transfer coefficient is H. Length of the fin is L and the cross section of the fin is circular. It is used to enhance the heat transfer from a surface wall maintained at 300 degrees centigrade. That means this surface wall value is given to me, that is TW is 300 degrees centigrade. The governing differential equation and the boundary conditions are given by K d2t over dx2 equal to P into H upon AC T minus T infinity. This is the governing differential equation for this particular problem, and the boundary conditions are given. That is, the essential boundary condition given is T of 0 is equal to TW, which is 300 degrees centigrade. That means value of temperature T will be equal to wall temperature, which is nothing but 300 degrees centigrade when X is 0. X is what? X is nothing but the length of the beam, which is varying from X, length of this fin, which is varying from X equal to 0 to X equal to L. So this is the essential boundary condition given in the problem. The natural boundary condition given in the problem is dt over dx, that is temperature gradient. Dt over dx is 0 when value of x is L, and we also call this dt over this component as, that means the end tip of the pin fin is insulated in nature, then only your that temperature gradient will be 0, that we know. So this is your natural boundary condition, where K is what? K is coefficient of thermal conductivity in the given differential equation. P is the perimeter of the cross section of the fin. AC is the cross sectional area of the fin. H in this expression is convective heat transfer coefficient. TW is wall temperature given. This is TW, wall temperature. T infinity is the ambient temperature. This is your T infinity, ambient temperature. And thus that ambient temperature value is given to you, that is 30 degrees centigrade. Value of K, that is coefficient of thermal conductivity, is given as 200 watt per meter per degree Celsius for aluminium. That means this fin is made up of aluminium. And value of convective heat transfer coefficient is given as 20 watt per meter square degree Celsius. Estimate the temperature distribution in the fin using Galerkin method. That means fin is starting from this end and is ending over at this end. Within the entire fin, if you treat this fin as one single element, then how the temperature distribution will vary? You have to find out one approximate temperature distribution profile by Galerkin method. Is the problem clear? Is anyone having any kind of doubt in this problem? Is the problem clear? What we want to find it out, what all data are given to us, and how we will proceed. Is everything clear? Please respond.
जी सर जी सर
Okay. So let us solve the problem. We have to solve this problem by Galerkin method. So very first step is identify the given differential equation satisfying the given problem. That differential equation is this equation: K d2t over dx2 is equal to P into H by AC T minus T infinity. Equation number 1. Now, since all the values are given to me in this problem, that means value of K, value of H, AC and P, as well as T infinity, all these values are given to me in the problem. So in the original differential equation, let us substitute these values and find out one modified differential equation from the given differential equation after substituting the values of K, P, H, AC and T infinity. Fine. What is K? K given in the problem as 200 watt per meter per degree centigrade. Substitute. So 200 into d2t over dx square is equal to P. P is what? P is perimeter of the fin cross section. Since the cross section of the fin is circular, so perimeter will be the circumference 2 into pi into r. See, 2 into pi into r into h. H is convective heat transfer coefficient given in the problem as 20 watt per meter square degree centigrade. So into 20 divided by AC. AC is what? Cross sectional area of the fin. Since the cross section is circular, so the area will be pi into r square into T minus T infinity. T infinity is ambient temperature given in the problem as 30 degrees centigrade. So substitute this value of T infinity by 30. Now if you see the second equation, in this equation I can cancel out pi and I can cancel out one r from denominator and one r from numerator. Then the resulting differential equation becomes 200 d2t over dx2 is equal to 20 into 2 is 40 divided by r, radius of the fin of the cross section of the fin. In the question, it is given that it is a 1 millimeter diameter. That means radius will be 1 by 2, that is 50 millimeter. But you have to convert that millimeter into meter. Why? Because see, all the values, whether it is k or h, everything is given in meter. So that 50 millimeter, multiply it with 10 to the power minus 3, it will be in terms of meter. See, 0.5 into 10 to the power minus 3 into t minus 30. 40 divided by this value is how much? 80,000 into t minus 30. Now then I can write d2t over dx2 is equal to 80,000 divided by 200, which is 400 into t minus 30. Equation number 2. Equation number 2 is the more modified form of the given differential equation number 1 after substituting all the possible values. So now we will use equation number 2 further in my calculation to find out the value of domain residual. Is equation number 2 clear till equation number 2? Any doubts? कोई डाउट है किसी को इक्वेशन नंबर 2 तक? Please respond whether it is clear or not till equation number 2. Hello. Hello. Please respond whether it is clear or not till equation number 2, or else I cannot proceed if you won't say yes or no.
हाँ सर क्लियर है.
Okay. So now what we need to do, we need to apply the trial function in order to solve this problem by Galerkin method. So we have to choose a trial function. See, in this given problem, trial function is not given to you, but in the last problem, trial function was given to you. Fine. So can anyone tell me that for this particular heat transfer problem, that is for this particular governing differential equation, what can be the nature of trial function? Whether I will take the polynomial trial function or I will take the trigonometric trial function. And if I am taking polynomial, which order polynomial trial function I will take, or if I am taking trigonometric function as a trial function, then which function will I take? Whether I will take the sine function, cosine function, or tan function. If anyone can respond, which trial function will I take? If nothing is given in the problem about trial function, fine. Better to go with polynomial trial function. Why? Because at last you will be integrating all these things. So integration of a polynomial function is quite easy as compared to trigonometric function. And so now it is decided that we will be taking the polynomial function as the trial function. Now the next step is which order polynomial equation we will take, whether we will take the linear polynomial equation, or we will take the quadratic polynomial equation, or we will go for cubic polynomial or some higher order polynomial. So can anyone say that which order polynomial expression we will take or we will use as a trial function? In order to assume the trial function, you have to look at the governing differential equation. This is your governing differential equation. Highest order of this governing differential equation is 2. So better to take a polynomial function of second degree or second order, which is nothing but a quadratic polynomial. So let us assume a quadratic trial function or trial solution, which is nothing but t cap of x near about equal to t of x, and that is c0 plus c1x plus c2x square, where c0, c1 and c2 are the unknown constants which we need to find it out by applying the given boundary conditions. That is equation number 3. Is it clear till equation number 3? Any doubt? Is it clear till equation number 3? Any doubt?
No, sir.
Okay, fine. So we are having two boundary condition. My essential boundary condition is this one, and my natural boundary condition is this one. So let us use firstly the essential boundary condition to find out the unknown coefficients. So the boundary condition is value of t will be 300 degrees centigrade at x equal to 0. So this is the expression of t cap of x, which is my assumed trial solution. So value of this value will be 300 when x is 0. So x is 0 means c0 plus c1 into 0 is 0 plus c2 into 0 square is 0. That means by substituting the essential boundary condition, I get the value of c0 as 300. This is the value c0 is equal to 300. Fine. So now the equation, you got the value of c0, you need to find out what c1 and c2. We are having one more equation, that is this natural boundary condition. From this natural boundary condition, now see, boundary condition is 1. Already we have used this boundary condition. Now we cannot use it. The second one is this natural boundary condition. So you are having one boundary condition and two unknowns, that is C1 and C2. So what we can do is that with the help of this natural boundary condition, either we will write C1 in terms of C2, or we will write C2 in terms of C1, and we will try to make the trial solution, and that means the coefficient which will be present in this trial solution, as a single unknown coefficient. It can be in terms of C1 or it can be in terms of C2. So let us apply the second natural boundary condition, that is dt of dx will be 0 when x is L. For that, I need to differentiate my assumed trial solution. So let us differentiate is dt over dx is equal to this c0, its constant, so no differentiation, plus c1 into dy dx of x is 1 plus c2 into dy dx of x square is 2x. So it will be c1 plus 2x, c1 plus 2c, c1 plus 2c2x, which is equation number 4. Now in this equation, let us substitute the natural boundary condition, which is dt over dx, that is nothing but dt cap over dx will be 0 when x is L. So put this value 0 when x is L. That means 0 is equal to C1 plus 2C2 into L. So I can write C1 is equal to minus 2C2 into L. So by the help of this natural boundary condition, I am having two unknown constant, that is C1 and C2. So I have replaced one unknown constant with the other one. So I have written C1 in terms of C2, that is minus 2C2 into L. Now what we will do is that we will substitute this value of C1 and C0 in the assumed trial solution. So the new trial solution becomes T cap of x is equal to C0, which is 300. C0 is 300 plus C1, C0 is yes 300 plus C1 into x. C1 is what? Your C1 is minus 2C2 into L, minus 2C2 into L into x plus C2 into x square. Take C2 common, so the resulting trial function becomes T cap of x equal to 300 plus C2 common x square minus 2lx, which is equation number 5. Now this is the modified form of your assumed trial solution in terms of one single constant C2. Is it clear? Equation number 5. Any doubt in equation number 5? Hello. Please respond whether you are having any kind of problem or not till equation number 5.
No, sir. No, sir.
Okay, fine. So next step is what? Next step is computation of domain residual. How I will write the domain residual? For that, in the original differential equation, that is this differential equation modified version, in this expression I have to replace t by the approximate solution, that is t cap of x, and I have to keep, or I have to place the right hand side towards the left hand side, and then I will equate this differential equation to 0. That means my residual will become r is equal to d2 t cap over dx2 minus 400 of t minus 30 equal to 0. See, our domain residual becomes d2 t cap over dx2 minus 400 t cap minus 30. Fine. So d2 t cap over dx2 minus 400 into t again you have to replace it by t cap minus 30, which is equation number 6. This is the domain residual of the problem. Is it clear?
Yes, sir. Yes, sir.
Fine. Okay. So according to Galerkin method, what I have to do? I have to integrate the product of weighted function, which is nothing but the trial function, with the domain residual. That is, my domain residual is this particular value. Fine. So in order to substitute this domain residual in this Galerkin method, first what I will do is I will remove this differential term, that is d2 t cap over dx2. For that I have to double differentiate equation number 4. I have to differentiate equation number 4. If you differentiate it, it will be d2 t cap over dx2 will be equal to, this is constant, so 0 plus 2 times of c2 into d by dx of x, that is 1. So ultimately your d2 t cap over dx2 becomes 2c2. Fine. So again you can modify your residual. Now your residual RD becomes, in place of D2 T cap over dx2, you can write 2 times of C2. So 2C2 minus 400 in bracket T cap minus 30. What is your T cap? T cap is equation number 5. Modified assumed trial function. So in place of this t cap, substitute this value 300 plus c2 in bracket x2 minus 2lx. x2 minus 2lx, then minus 30. So if you solve it further, fine, just open the bracket and just solve it further. The final domain residual, which you will find it as 2 times of c2 minus 108,000 minus, plus minus is minus 400 x square c2 minus minus is plus 400 into 2 is 800 lx c2, which is equation number 7. And this is your modified form of domain residual. Now if you see in this particular domain residual, fine, the unknown is C2. If by Galerkin method, if I find out the value of C2, fine, then I can get the solution of the problem. So is it clear till equation number 7? क्या कोई doubt है equation number 7 तक किसी को? कोई doubt किसी को equation number 7 तक? Hello. Please respond whether there is any doubt or not till equation number 7. Hello.
No, sir. No, sir.
Okay, fine. So now I have to minimize this domain residual in order to get the solution of the problem. That means minimization of domain residual means finding out the value of this unknown parameter C2. So I have to use which method? In the question it has been told to you that you have to use the Galerkin method. Then according to Galerkin method, you have to multiply the residual of the problem, which is equation number 7, with the weighted function of the problem, and this weighted function is my given assumed trial solution of the problem. So equation number 5 is my modified version of assumed trial solution. Why I am not using equation number 3? Because if I use equation number 3, there will be 3 unknowns. C naught, sorry, C naught is known. There will be 2 unknowns, C1 and C2. I cannot solve the problem. So I am going for this modified trial function in which there is only one unknown, that is C2. So just multiply equation number 5 with equation number 7. So your final expression becomes integral 0 to L weighted function, which is the modified form of the trial function, that is 300 plus C2, 300 plus C2 in bracket x square minus 2lx into domain residual is equation number 7, that is 2C2 minus 108,000 minus 400 x square C2 plus 800 lx C2. Fine. Now just solve this integral equation. Simple algebra is there, and once you solve, you will get the value of unknown parameter C2, and that is coming out to be 38751.43. Now if you substitute this value of C2 in the original assumed trial function, that is this trial function C0 plus C1x plus C2x square, fine, you will get the value of your approximated solution of the problem, which is t cap of x, that is t cap of x is equal to 300 plus C2. So 300 plus C2 is 38751.43 into x square minus 2lx. X square minus 2lx. So this is the final temperature distribution inside the fin if you treat the entire beam as one element by Galerkin method. Any doubt in this problem? Any doubt in the problem? Hello? Hello? Please reply whether the problem is clear or not.
Yes, sir. Yes, sir. Actually, sir, I am taking my lunch at that time, so
Okay, okay, okay. No,
I'm using
see, if
my
you will
phone.
not respond, that I will think that no, there is some problem. I cannot go further.
Yes, sir.
Okay, 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 fine. So you can expect such type of problems in this method. Which method? That is this particular method. Wait. Yes, weighted residual method. Four different methods are there. You can expect such kind of problems. Fine. And one more problem, which I have told you in the last class, that there will be no differential governing differential equation. There will be no essential, no boundary condition. There will be no trial function. Just the problem statement will be given to you. According to that problem statement, first you have to frame the governing differential equation. You have to frame the boundary conditions, you have to frame the trial solution, then you have to find the approximate solution by any of these techniques. With this, we have completed this weighted residual method. Last method which is left is Rayleigh-Reid's method, which is one of the form of variational method. With this method, we will complete this module. Fine. So before starting the concept of Rayleigh-Reid's method, first let us understand. I will take 10 more minutes because there is a small topic. I will complete that small topic, then you all can leave. And that is your potential energy approach in FEM, because we will be using this concept to solve the problems related to Rayleigh-Reid's method, and this concept will be used in second module also. So better to understand first of all what is this potential energy concept in FEM. See, this Rayleigh-Reid's method, it is what? It is a variational method or variational approach to find out the approximate solution for a given problem. But in this method, what we do is that we write the governing differential equation in terms of integral equations. See, again I am repeating. What is a variational approach? Rayleigh-Reid's method is nothing but a part of variational approach. In variational approach, what we do, for example, let us take this problem. Which problem? This heat transfer problem. In this problem, governing differential equation is given to you. You start with the governing differential equation, then you find out the residual, and then by different methods you find out the approximate solution of the problem. But in variational method, the governing differential equation in the very first step is converted into an integral form or integral form of equation. Then you minimize that integral by some technique. That technique is your Rayleigh-Reid's method. So these are the two difference between weighted residual method and variational method. In weighted residual method, four different methods are available. In those methods, what is happening? The governing differential is given to you, and you use this governing differential equation further to minimize the problem. But in variational method, the governing differential equation is converted into an integral form or integral form of equation, then by certain methods you try to minimize that integral equation to get the approximate solution of the problem. This is the basic difference between the variational approach and the weighted residual approach. Is it clear? क्या कोई डाउट है? Hello. Is the step clear? Difference between variational approach and the other approaches which we have done, which we are doing from past few classes? Any doubt? Please respond once whether any doubt is there or not. Hello. Hello. Please respond whether any doubt is there or not. Difference between variational approach and the approaches which we are doing from last few classes. Okay, if no one is responding, then I will assume that the thing which I have discussed now, it is clear. Fine. So before starting that Rayleigh-Ritz method, first let us understand what is this potential energy concept or potential energy approach in FEM, because we will be using this potential energy approach to find out the approximate solution by Rayleigh-Ritz method. Now what is this potential energy approach? The principle of minimum total potential. That means in this approach what we do, we find out the total potential energy of the given problem by the concept of principle of minimization. What is this concept? The principle of minimum total potential energy states that for a system to be in equilibrium with all possible displacement satisfying boundary conditions, the total potential energy of the system is minimum. That means for a particular problem, if in that particular problem, due to application of some external load, if the nodes or the element is displacing, then the total potential energy of the problem is minimum. That means if pi is the total potential energy of the problem, then this pi can be written as the summation of internal energy stored in the given problem plus the external energy of the problem. And sometimes this pi is also known as potential function or simply potential. There are three names of this pi. You can call it as potential energy. You can call this pi as potential function. You can call this pi as simply potential. So this potential is what? It is the summation of internal energy plus external energy. Internal energy stored in the body is nothing but the strain energy. That is U. It is nothing but the strain energy of the body plus external energy. External energies are all negative in nature. That means you apply these energies to the body. And if you know the concept in thermodynamics that work done on the system is positive and work done by the system is negative. So what are these external energies? In these external energies, energy is what? Energy is force into displacement, that is total work done, that is your energy. The force which are acting on the body, which are constituting these external energies, that is the external forces acting on the body. So by that sign convention concept, we are taking all the external energies acting in the body to be negative. So your final equation becomes pi is equal to U minus W. Is it clear till this point? Pi is equal to U minus W. If it is clear, then I will proceed further. I will take 5 to 10 minutes maximum more. I will complete this potential energy topic, then I will make you leave. So can you please tell me whether this equation is clear or not? Pi is equal to U minus W. Hello.
Yes, sir. Yes, sir.
Fine. Okay. So what is pi? Pi is my potential or potential function or simply function or potential energy. And in Rayleigh-Ritz method, the very first step is to find out the potential function of the given problem in integral form and then minimize that potential function. That is the main concept of Rayleigh-Ritz method. Fine. So pi is equal to U minus W. What is U? U is the strain energy stored in the system. And what is your W? W is nothing but the work done by the external forces acting on the body. And by the sign convention concept, that is work done on the body is positive and work done by the body is negative. Since you are providing external forces on the body, then the body is doing work. So that's why I am taking all these external energies to be negative. Fine. So now we have to substitute the values of U and W. W in the potential function. Fine. What is U? U is strain energy stored in the body, and I know that the strain energy is what? Half into stress into strain. But I told you that this potential energy approach, which we will be using it in Rayleigh-Ritz method, it is nothing but a variational approach. So we have to convert the normal equation into an integral equation. So we know from the strength of material concept that strain energy is what? U is half into stress into strain. So let us write that same equation in integral manner. So it will be volume integral of half times of stress into strain into dV. This is stress into strain into dV. You can take the half outside the integral. So U is half times of volume integral of sigma t into epsilon t dV. Now what is this sigma t and epsilon t? Sigma t and epsilon t are stress and strain vectors. Now this sigma t and epsilon t can be, if you are only taking sigma along x-axis, it will be sigma xx. If you are taking along y-axis, it will be sigma yy or sigma zz or tau xy shear along xy plane or tau yz or tau zx. It can be anything. So it is nothing but a sample space. Sigma is a sample space of these 6 elements. Similarly, epsilon is what? Epsilon is your strain vector. It can be, if you are talking about x-axis, it will be epsilon xx. If you want to find out the value of strain along y-axis, it will be epsilon yy, epsilon zz. Likewise, shear strain gamma xy, gamma yz, and gamma zx. That means this epsilon is what? It is a set containing these 6 values. Is it clear? This expression U is equal to half times of volume integral sigma t into epsilon t dV. Any doubt?
No, sir. No, sir.
Okay, fine. So according to my problem, if my problem is 1D, accordingly we will select what will be the value of sigma and what will be the value of epsilon. If my problem is 2D, then I have to consider the 2D plane. If my problem is 3D, then all the elements I have to consider while finding out the potential of any problem. Fine. So this was all about this strain energy. I told you that the potential is nothing but the summation of internal energy, which is the strain energy, and the external energy. What are these external energies? These are work done by the external forces acting on the body and are negative in nature. So let us find it out. What is the value of this W? So this W normally for a static structural problem consists of three main things. This surface integral of ut into tt into ds minus surface volume integral of ut into bt into dv minus summation of I ui of t into pi. Now what are these three things? This first integral is nothing but the traction work done due to traction force in the body. This first surface integral is nothing but the work done due to traction force acting in the body. And what is your traction force? Traction force is that force which you are applying on the surface of the body. For example, UDL, uniformly distributed load. You apply it on the surface of the body. That is a traction force. Again, why I have written T of T? I have written T of T because it is a vector comprises of tx, ty, tz. If that particular traction force is applied along x-axis, you have to take the tx value. If it is applied in y-axis, you have to take the ty value. If it has been applied in z-axis, you have to take the tz value. Fine. And what is this second term? Second integral, that is volume integral of ut into bt into dv is what? It is external work done due to body force. This B is your body force. This T is your traction force. So the second integral is nothing but the external work done on the body due to body force. This BT is body force. Again, if you consider a 3D body, then you have to take all the three body force, that is bx, by, bz. Or if we are talking about 1D, then you can take that one dimensional body force. Now what is this body force? This body force is that force which is applied on the entire volume of the body. For example, self weight of a bar. Self weight of a bar is what? That is the weight of the bar itself, which is applied on the which is applied on its entire volume. So that is an example of self weight of the bar. And what is this third component? This is the external work done due to point load acting on the body. That means if you are having a beam, in that beam, if at any point a point load is acting, fine. For example, wait. For example, mm, just wait for a second. Can you see my white screen? Can you see my white screen?
Yes, sir.
Okay. So let us see. See, say this is your problem. For this problem, you have to find out the potential energy. That means this is a simply supported beam. That means you have to find the potential of this problem. So say in this beam, this is node point 1, this is say nodal point 2, and this is nodal point 3. That means this element is comprising of two elements. Node 1 and 2 comprises first element, node 2 and 3 comprises second element. If on node 1 and 2 UDL is applied, the intensity of this UDL is say 4 Newton per meter, and the entire length of the beam is say for 2 meter. 2 meter, fine. And at the nodal point 2, at the node, or else let us take one more node, that is 3. If this is 3, then this will be 4. Now the entire beam is divided into 3 elements. The first element comprises of nodal point 1 and 2. Second element nodal point is 2 and 3, and for the third element nodal extreme 2 nodal points are 3 and 4. So on this third nodal point, if I applied a point load P3, then for this particular problem, how I can define my potential? I can write this potential as pi. Pi is what? Pi is equal to strain energy minus W, and that W is work done due to all external forces. So I told you that first term is what? First term is work done due to traction force. That means that force which you apply on the surface of the body. So by looking at this problem, I can see that the traction force is nothing but my UDL. So this magnitude of this UDL is nothing but your T into U. U means deflection of that particular element where that UDL is applied. This will be your traction component of work done minus, this is your work done due to body force. If I have not told in this problem that there is any body force, that means if the self weight of the beam is not taken into account, I will not take that body force. If the self weight of this beam is taken into account, then I will take that body force and then I will integrate it. And the last portion is this your work done due to point load. Fine. What is this I? I represent the node where you are applying the point load. So if I see this problem, in this problem I am applying a point load P3 in downward direction at node point 3. So for this particular problem, work done due to the external work done due to point load will be U3, because it is that load is applied on nodal point 3. So your node 3 will deflect due to that point load into P3, into P3. That we, and this force P is applied on the nodal point 3, so it is P3, and this is third nodal point. So with this is a simple example, you can find it out the overall potential of this problem, and then in Rayleigh-Ritz method we will minimize this potential to get the approximate solution. Is it clear? क्या समझ में आया? ये क्या है? ये W traction component, that is work done due to traction component, work done due to body force component, and work done due to point load component. Is it clear? Any doubt? कोई doubt है?
No, sir. No, sir.
Fine. So I'll take 3 to 4 minutes more. Last slide. Fine. Again, see, U is also a vector here. U is also a vector, because if you are talking about 1D, in one dimensional, say the displacement of the problem is U. In two dimension, you will have two displacement, one along x-axis, one along y-axis. If along x-axis displacement is u, along y-axis displacement is v, along z-axis displacement is w, then whatever is asking in the question, you have to take that particular displacement and you have to solve the problem. And what is pi? Pi is your point load applied at a point or node along the bar. Fine. Now, what will be the value of u and w for different type of problem? Normally we solve or we try to minimize the error function by Rayleigh-Ritz method for beam problem, for a bar problem, and for a spring problem. So for a beam problem, if a beam is given to you, that means this beam, if a beam is given to you, this is your beam, and due to some external load the beam is deflecting, then for this problem how you will formulate your pi? In that case, pi will be U minus W. U is what? U is strain energy stored in the beam. Already you have read in strength of material that if a beam is given to you and if that beam is bending, what will be the formula of that strain energy? But here I have to write that formula of strain energy in terms of integral. In term of integral, that formula is nothing but half E into I integral of d2y over dx2 whole square into dx. And point load will be what? Point load is again load into deflection. So here is this load, in here I have written that load by W, and this deflection is nothing but Y. So I have written in place of U Y into dx. Fine. So sorry, this is for UDL. UDL, integral of W into Y. That means if this particular value is W, and due to this UDL, the deflection in this particular section, in this particular element is, say, it is varying in terms of Y, then that is that value of Y. And what is this and what will be point load in this beam problem? It will be load means simply this load into that particular node where that load is acting. So Pi into Ui. See, Pi into Ui. Here U is nothing but Y. Similarly, for a bar problem, that strain energy becomes half times of E into A integral of du over dx whole square into dx. And point load, if I assume that there is no UDL, that means no traction component, no body component, only point load is there. Point load, again, it is very simple. W is equal to load which is acting at particular node into the deflection of that particular node where that point load is acting. And for a spring problem, you will be what? You will be half into K into delta square. That means if I am having a spring, say this is a spring, this is, say, node number 1, this is assume node number 2, and this is one element of a spring. Then for this spring I can write, or I can formulate the potential as pi is equal to U minus W. U will be half K into delta square. Delta is the deflection, that is U2 minus U1. Delta is the overall deflection, and if you assume that the deflection at node 2 is greater than that of node 1, then you will write U2 minus U1. Or if you find that the deflection of node 1 is more than that of node 2, then this deflection will become U1 minus U2. So this is your strain energy, and your work done due to point load is again P into Ui. So on the basis of different types of problems, I have to use different equation for U and different equations for W. That means different equations for traction, work done due to traction force, work done due to body force, and work done due to this point load. With this potential energy concept is over. Then in the next class we will be straight away starting the Rayleigh-Ritz method. So in Rayleigh-Ritz method, the very first step is what? Very first step is formulation of potential for any problem. Then we have to minimize that potential to find out the value of unknown constant. Then that particular unknown constant we will substitute in the given trial solution to get the approximate solution for the problem. Is it clear? Any doubt? Hello?
Yes, sir. Yes, sir.
Fine. Okay. So with this, I end my lecture over here only. Again, we will meet in the next class. Till then,
Okay,
thank
sir.
you. Okay.
Okay, sir.
Thank you.